This is the video on section 3.1 where we're going to be dealing with quadratic functions, quadratic models, and we're also going to be looking at an introduction to polynomials. So the very first thing I want to do is have you look at what a polynomial might look like. I've given you an example of a pretty ugly polynomial. I did not write it in such a way where my exponents decrease. Normally we would write this in order where the highest power goes first and the constant, the number without a variable, goes last. But I, on purpose, chose to write this one a little differently. The one thing that I'd like for you to do is I'd like for you to pause the video and really pay attention to a couple of things. I want you to pay attention to what the leading coefficient is. I want you to pay attention to what the highest power is, called the degree. Also, what is the leading term? I've been using the word terms on you all semester, so you should be fairly familiar with this. So pause the video and just get yourself familiar with each of these pieces. All right, now that you're back, let's go ahead and take a look at a couple of different examples that we might have. So the very first example, you notice it just says f of x is equal to 2. And this is just simply going to be a constant function. Its degree, its highest power is 0. Because remember, this is the same thing as 2 times x to the 0 power. And the leading coefficient, remember, that is going to be the coefficient that's in the term along with the degree. And so my leading coefficient is going to be 2. My second example is going to be linear. There's no powers there, so if I were to graph it, it would be a line. My degree, my highest power is 1. Leading coefficient is 5. For the third example, this is a quadratic. We're getting pretty used to dealing with quadratics. We've done this a good bit now from chapter 2. The degree is 2, and the leading coefficient is 4. Now I want to stop right here and point out that every single time the leading coefficient happens to come first. But if you go back to the example, the leading coefficient was not written first. Now that was because I chose to write it in a way that isn't normal, but just understand that the leading coefficient isn't always necessarily written first. You need to go to the term that has the degree in it to find that leading coefficient. My next example is what we call a cubic, because the highest power is a cube. Its degree is 3. My leading coefficient is 2. And the last example is a quartic, because the highest power, the degree is 4. And the leading coefficient here is 1. Now let's specifically spend some time talking about just the quadratics. So this is going to be just the one that has the highest power of 2. This is the only one that I'm really going to focus on for the rest of this lesson. So the quadratic is a function that has the form ax squared plus bx plus c. You've actually seen this a couple times. Some graphing techniques that we've already talked about back in section 2.7. So just take a look at this graphic and you'll recognize I didn't give you the same graphic in section 2.7, but all of the material we talked about in section 2.7. So I'm going to go ahead and go down to example number 1. Now example number 1 says to graph the function and give the domain and the range. And so I've given you a little hint here. Let's go ahead and graph it in the calculator. And we're going to use the table of values. So let's go to the calculator. And I've already entered mine into Y1. And when you look at a graph, this is just a very common parabola. And what I'm going to do is I'm going to look at the table of values. Now, in order to this, you need to push the second button and the graph button. Notice right up above graph, it says table. And this is going to give us a table of values. So I'm going to use this table of values to be able to graph. I didn't choose every single value there, but taking my table of values, we're going to graph what we have. And I've already marked mine out. And I didn't graph every single coordinate. I only graphed 5 of my coordinates. All right, so then we need the domain, which is going to be all real numbers. And my range, well, the bottommost value is a -8. and the topmost value continues on forever. For the second example, we did these back in section 2.7, so you don't need a calculator on this one. Just think of a description of what happens to the parent. So our parent here, hang on just a second, there we go. Our parent has a vertical stretch of 2, and it's also being reflected over the x-axis. And so you'll notice that I've got coordinates that are already marked out. My first coordinate here is that 0, 0, no big deal there. Because it's reflected, it's going to go down. And notice that we're going to go to the right one and down one. To the right one and down one is what the parent does. But this guy, notice, is going to go down 2 because of that vertical stretch of 2. All right, and so not only that, we're going to go to the right 2. Parent went down 4. We're not going to go down 4. We're going to go double that. We're going to go down 8. So everything that the parent does ends up being double. All right, we can do letter C the exact same way by using what we learned in section 2.7. And so we've got a vertical stretch of 2. We have a reflection over the x-axis, just like we did in the last example. The inside tells me to move to the left 3, and the outside tells me to move up 5. So you'll notice that the very first thing I did here was I moved left 3 and I moved up 5. And that's where my vertex is. And then at that point, I am reflecting down. So we're going to go right 1 and down 2, again, because of that vertical stretch. Left 1 and down 2 as well. And then we're going to go right and left 2, down 8. Very similar to the one that we just did. And if I were to compare the two graphs, which is what part C tells me to do, I'm going to notice that they're the exact same graph. It's just that the second one is moved left 3 and up 5. All right, then we can talk about completing the square. We did completing the square back in chapter 1. I made a big deal about it in chapter 1, so hopefully you have been able to practice that at least back in chapter 1. And what I'm going to do here is, first of all, I'm going to complete the square. It's going to look a little different because when we completed the square back in chapter 1, often it did not say f of x equals, it said 0 equals. So this is going to look slightly different, but all of the concepts are going to be exactly the same. So I'll walk you through those. All right, so the first thing I'm going to do is I'm going to add 5 to both sides. I know that you can't do f of x plus 5, but basically I'm just holding it over on the left side temporarily. And after I've added 5 to both sides, this is where I'm going to take half of b, square it, and add that to both sides. So half of b is 1. When I square 1, I get 1, and so I'm going to add 1 to both sides. And then I'm going to factor my trinomial on the right side. On the left side, I will combine my like terms. So the 5 and the 1 become a 6. Factoring my trinomial gives me x plus my half of b, quantity squared. And now that 6, I can go ahead and move it back over to the right side. Excuse me. Now, when I look at this, this looks a lot, I'm able to see which direction to move. I couldn't see that when I was looking at the equation in this form. And so I know now that I'm going to move to the left 1 and I'm going to move down 6. Other than that, it's going to be a totally normal parent parabola. And so you can see on my graph over here that I've moved left 1 and down 6 to get to my new vertex. And from there, I went right, left 1, up 1, just like the parent does. Right, left 2, up 4, just like the parent does. Now, I'm also asked to give the intervals of increasing and decreasing. So you'll notice that as you move from left to right, the first thing that's happening is you are decreasing, and you're going to be decreasing from negative infinity to negative 1. Remember that when you do increasing, decreasing, and constant, you're never, ever, ever going to use square brackets. And then secondly, you're always, always, always going to use x values and only x values. Don't use any y values. After I get to that vertex at the x value of -1, then I'm going to turn around and start increasing, and I'll be increasing from -1 to positive infinity. All right, on the next example, we're going to do this one on the calculator as well. And so we're looking here, first of all, we're asked to identify the intercepts of the graph, and we're going to find the y-intercepts by hand, but we're going to use the calculator to get the x-intercepts. So before we enter this into the calculator, let's just go ahead and get our y-intercepts. And remember, if I have any kind of a coordinate on the y-axis anywhere, all of these coordinates have one thing in common. They all have an x value of 0. And so in order to find a y-intercept, I just need to let x equal 0. And when I plug that into my equation up here, my x value being 0, I'm going to get a -6 out. So I went ahead and I drew this on my graph before I even entered it into my calculator. So I have that coordinate 0, -6 down at the bottom. Now to get my x-intercepts, we're going to go to the calculator. So let's go ahead and run over here. And the first thing you want to do is go to y equals, clear out anything that might be in y equals, and let's go ahead and type in 2x squared plus x minus 6. And we can go ahead and graph that. I personally have the standard window, so you remember you can get to the standard window by doing zoom 6. I like the standard window best. Now, you're going to notice that there are 2 x-intercepts that we need to find. There are keystrokes. There's a keystroke video on my lab under your video and resource library. So in order to find x-intercepts, or what they are also called zeros, you can go to that video. I'm going to run through this pretty quickly. So if you know how to do this, this is going to make sense. If you haven't done this before, you'll want to go back to that particular video. It's not in my playlist. It's just a separate link that has nothing but calculator keystrokes. So what I'm going to do is I'm going to go to second, trace, and I want to go to option number 2, which is finding zeros. And you're going to be asked to find a left bound. What I'm going to do is I'm going to arrow to the left until I'm on the left side of my first 0, the left side of my first 0. Unfortunately, I cannot actually show you this on the screen because of the fact that it won't let me show you. There's no highlighter or laser dot or anything. So I'm on the left side of that first leftmost 0, and I'm going to push enter. And you can see there on my calculator, it shows me a red vertical line that I'm on the left side of that 0. And now it's asking me to go to the right side of the 0. So I'm just going to arrow a little bit to the right. And now I'm on the right side of that 0. I'm going to push enter. Now your calculator is going to ask you to guess. You don't need to guess. So you can just push enter a third time. And you're going to notice that I have a 0 at x equals -2. So I'm going to go back to the notes. And one of my x-intercepts is going to be at x equals -2. You see here that I've already put it on the graph. Now, I didn't uncover that yet because both of them are hidden. So let's go back. And now we need to find the other 0. So I'm going to go back to second, trace. Again, I want to go to option number 2 for 0. I'm going to arrow over to get closer to my other x-intercept. And I'm on the left side of my x-intercept. I'm going to push enter. And then I'm going to arrow a little further to the right so that I'm on the right side of my x-intercept. Push enter again. Yours will ask you to guess. You can push enter. You don't need to guess. And you'll notice that the other 0 is going to be at 1.5. And so I've got that marked on my graph. Both of my zeros then at -20 and at 1.50. Now, sometimes my lab asks you to put these in coordinate form. So make sure if it does that, that you have the right format. And then I've got enough information now to be able to graph this. Now, there's something that I want to point out here. Let's go back to that graph. You'll notice that the y-intercept is not the minimum value. So my y-intercept, notice that to the left of the y-intercept, it goes a little lower. So just understand that you're not at the leftmost value there. So I'm going to go a little lower. Whoops. Doesn't work so well with an eraser. All right, so it might look something kind of like that. Okay, the vertex formula is next. So this is kind of a shortcut, something that allows you to not have to complete the square all the time unless the directions say so. And please understand, if the directions tell you to complete the square on a test, I'm going to be looking on your work that you completed the square on the test. But the vertex formula is pretty nice. It tells you that to find, well, let me say it like this first. When I am finding a vertex, I'm going to drop down to this gray box for just a minute. When I'm finding a vertex, the vertex is always going to be at the coordinate HK. I uncovered there number one, part of number one. The vertex is always going to be at HK. So when I use H's and K's, I want you to understand where I'm getting that from. So back up then to the vertex formula. To get my H value, the X piece of my vertex, I'm going to just do negative B divided by 2A. And once I have the X value of my vertex, all I have to do is plug and chug to get the Y value of my vertex. And you'll notice in bold there, it says it's not necessary to memorize this expression because truly all you're doing is plugging in your X value to get your Y value. Now in the gray box, you've got the quadratic function here that I've already mentioned to you. I already gave that to you at the beginning of the video, ax squared plus bx plus c. This can also be written as a times the quantity x minus h squared plus k. And we understand that. We have used that back in section 2.7, and then we've used it some in this video as well, where your h value is going to be that negative b over 2a, and your k value is just going to be found by plugging in what you found for h. You're always going to be drawing a parabola. As I already said, the vertex is going to be HK, and the axis of symmetry will be x equals h. It's going to be opening up if my a value is positive, and it's going to open down if my a value is negative. The y-intercept is always going to occur at the coordinate 0, c. So if you go back up to this, if you plug in 0 for all of your x's, the only thing that's going to be left over is your c value. And the intercepts are going to be, the x-intercepts are going to be found by solving that quadratic equation, the one that we've seen so much already this semester, 0 equals ax squared plus bx plus c. All right, now let's jump into example number 4, and I'm going to introduce a bit of a new concept here. So we're asked to find the axis and the vertex of the parabola with the given equation. Well, the first thing I need to do is I'm going to use my shortcut. I'm going to use this to get the h value of my vertex, the x value of my vertex. I'm going to do negative b over 2a. And so negative b over 2a is going to be negative 12 over 2 times negative 3. And you clean that up and you're just going to get 2. Well, now that I have my h value of 2, all I need to do is plug that in to the original equation to be able to get my y value. Now, the work that I've shown here is called synthetic substitution. I'm actually going to make a separate video on this. The graphic walks you through it, and I'm going to use this graphic on the other video. All this is an alternate way of substituting, and it's actually a faster way of substituting. So that's what you see here. I'm not walking you through that particular work. That'll be on a separate video. All right, so I now have that my f of 2 is equal to 4 when I plug that in. I was asked for the vertex, so now I can actually write that the vertex is 2, 4, and my axis of symmetry is going to be at x equals 2. All right, the last question for this section is going to be height of a projected object. I've mentioned in class, and I think I've mentioned in videos, that this is one of the most common types of story problems that you guys are going to run into in Math 110. So you'll notice that you've got a ball. It's projected directly upward from an initial height of 75 feet with an initial velocity of 112 feet per second. Part A says that we should give the function that describes the height of the ball in terms of time t. Now, this is something that you haven't had to do yet. Every single time we've run into one of these questions, we've always given you the equation. But now you have to come up with your own equation. And the way that you're going to do that is you're going to use this right here, where you'll notice that v sub 0 is the initial velocity. And so we've been told that the initial velocity here is 112 feet per second. So we're going to put that number in for the v sub 0. And s sub 0 is the initial height. And so my initial height is going to be 75 feet. And so we'll plug that in. So I erased my 5. And so this is going to be the equation that we're going to use. All right, so let's go over to the graphing calculator to answer part B and part C. After how many seconds? Now, I want to stop right there because the first thing, even before I go to the calculator, is that we know that we're looking for a time. After how many seconds does the ball reach its maximum height? Well, this is vertex. So all we're doing is we're looking for the t value in the vertex, which is also the x value in the vertex. Now, you see here that I've actually done the work. So you can, spoiler alert, you can see the answer. I used my vertex formula to find the time value of the vertex. So after how many seconds does the ball reach the maximum? After 3.5 seconds. But let's look at how to do that on the calculator. So let's go over to the graphing calculator. And for y equals, let's clear out what's there. And let's type in our equation. So we have negative 16. We're not going to use t, we're going to use x. Negative 16x squared plus 112x plus 75. Now, unfortunately, the standard window is not going to work for this because you'll notice that I have things like 75 as the initial height. So this is going to be a pretty big window. And so what I'm going to do here is I'm going to keep an x min and max of negative 10 and positive 10. I'm fine with that. But my y maximum, that's what I'm going to change. My y maximum, I'm going to change to, I don't know, 300. My y scale, I'm going to change to 50. This is just going to draw fewer tick marks on my y axis, so it's a little easier to read. And then I'm going to go ahead and graph it. So what you've got then is a picture of the path of this particular ball. All right. And we want to find the maximum. We want to find the maximum. And so we'll go back to second trace. And again, if you go to my lab, there are keystrokes. There's a keystroke video for doing this. But we want option number 4, which is going to be maximum. We're being asked for the left bounds. And so I'm just going to start arrowing to the right. I'm not even really certain where I am at the moment. There we go. Okay. So now you can see my cursor there, and I just want to be on the left side of my maximum. Once I get there, I'll push enter, and then I want to arrow over to the right side of my maximum, and I'll push enter. You're going to be asked to guess, so push enter again. Now notice at the bottom of your screen, it says that your maximum occurs at the x value of 3.5. We already found that. And the y value is going to be 271. And again, if you look at my work there, you'll see that I plugged in the 3.5 and I got out a 271. So let's make this make sense then. After how many seconds does the ball reach the maximum height? It is going to be at 3.5 seconds. And then the second question says, what is the maximum height? Ball reaches 271 feet. So those are the two parts of that particular question. All right, for part C, for what interval of time is the height of the ball greater than 200 feet? All right, so we're going to go back to the calculator and go back to your y equals screen. And then for y2, let's just give a horizontal line of 200. Go to your graph, and you'll see there that I have this horizontal line at 200. And this is going to help me to find out the interval of time. So notice the top part of my parabola, that's all of the time that the ball is above 200 feet. And so what I'm going to do is I'm going to find the intersection of my two graphs. So yes, once again, let's go to second trace. Notice that number 5 says intersect. Now, I'm going to arrow to the left and get close to my first intersection point. So there's my first intersection point. I can't get right on it, but I'm close. And so I'm going to say yes, that's my, I think on your calculator, it's not asking you for a left bound. It's asking you for an equation. And so just pick one of the two equations. So I'm going to push enter. Mine says right bound. Yours is going to say the second equation, and it'll actually jump your cursor to the other equation. So push enter again. You won't want to graph. I'm sorry, you won't want to guess. And you'll notice that my intersection occurs at the x value of 1.39346. I'm going to come back to the notes, and I think I'm going to have to cover both of these at the same time. But 1.39, that's the first x value, that's the first time. 1.39 seconds is where the first time the ball hits 200. Now let's go and do the same thing for the other intersection. So back to second trace, option number 5, arrow over to the second point of intersection, push enter. You can push enter again, and then a third time for your guess. And you'll notice that the point of intersection now occurs at 5.60654. So that's going to be that second value that I have there, 5.61. So from the time of 1.39 seconds all the way up to 5.61 seconds, the ball is above 200 feet. The last question that I'm asked, after how many seconds will the ball hit the ground? Well, we understand, okay, so if this is a rough sketch of my graph, the ball's going to hit the ground right here. We need to find a 0. So let's go back to the calculator. And we need to find the 0 that's on the right side. So back to second trace. Go to number 2, 0. Be on the left side, the left bound. And go to the right bound. And okay, so on my app then, it's not liking that I have two different equations, so I need to get rid of my 200 equation before I do this. So back to second trace, go to 0. Sorry, and I was doing it in the wrong spot anyway. So go down close to the 0. I'm on the left side of the 0, so I'm going to push enter. And then I'm going to go to the right side of my 0, push enter again. And you'll notice that my x value is at 7.61552. So at 7.62 seconds, the ball hits the ground. All right, folks, so that wraps it up for this section. Be on the lookout for a video about synthetic substitution, hoping to get that loaded soon.